I'd like you to take a moment here before we get rolling in this problem and actually think through this one. If I wanted to get an upper sum for each of these, and each one individually, would I use right-hand endpoints or left-hand endpoints for each? All right, so when drawing these rectangles in, usually the best strategy is you basically are starting by drawing your lines at the intervals for your rectangles. So like this is the dividing lines between my rectangles here. Now, the question though is, for each of those rectangles, am I going to go to the left or am I going to go to the right from there? And in this particular question, it's asking us to have an upper sum. So that means I want to have extra rectangle, right? So in this case then, from each of these, I might go then to the right. Now, if I draw the rectangles like this then, are those right-hand endpoints or left-hand endpoints? And sometimes people have trouble with this idea, so just to be sure, let me isolate a single rectangle here. Now let's go with this one. And as you take a look at that rectangle, which side of this rectangle is actually hitting the graph? It's the left side, yes. And so in this particular problem then, this would be a left-hand endpoint. And so for this graph, a left-hand endpoint gives us an upper sum. Now we'd approach the second graph the same kind of way, where I would actually be drawing in the dividing lines between each, and then I would use those to draw the rectangles. In this case though, if I want extra rectangle, I go straight over that way, because that ends up giving me the extra rectangle there above the graph. Well, is that a left-hand endpoint or is that a right-hand endpoint? It is right. This is a right-hand endpoint here. And this actually is a general rule. It's demonstrating a general rule that we can know going forward. If we want to have upper sums, a left-hand endpoint will give me an upper sum when? When will it give me an upper sum with a left-hand endpoint? A negative slope, yes, or you could say it's decreasing, you could say it's a negative derivative. There's tons of different ways. I'm going to go with decreasing. And similarly, a right-hand endpoint will give me an upper estimate if I have a graph that's increasing. Now, if you have a graph that is not consistently doing either, for instance, like a sine or a cosine kind of graph, something like that where it goes up and down, or if you have like a particular x cubed graph, something along those lines, if it's not consistently increasing or consistently decreasing over our interval, then we can't necessarily use this rule to know whether it's upper or lower. And so that's just kind of bringing back some ideas and pulling some ideas together. But it's not going to be our big idea of today. Our big idea of today actually goes back to the area under the curve. And so here's the problem that we looked at like 2 days ago worth of time here, where we had the equation y equals x squared, and we were trying to find what's the area under the curve, that shaded region, between x equals 0 and 8. So we were just looking at that. And remember on Friday, the work that we did on this is I started by demonstrating how we could estimate with n equals 4. That is 4 different rectangles. And then after I did that one, then you went and did it with 8 rectangles. And then we looked to see, okay, how can we even get a better estimate? And there were a number of different methods that people used. One of those methods was just making more rectangles. And each time we did it, we had less and less wasted space up here, extra space that we are counting out of each rectangle. So we're getting closer and closer to the actual value, to the actual area that was under the curve. The big question today, though, is how many rectangles would I need in order to hit the exact value? Would 1,000,000 be enough? Well, a million would be certainly pretty good, but it wouldn't be exact, right? Because we'd still have wasted space, so they're just tiny little bits, a million tiny little bits extra. Really, there is no number. I mean, the bigger it is, the closer we get. But if we're getting bigger and bigger, really that means we're approaching infinity. But then, how can we deal with this? Because we can't really have an infinite number of rectangles. You certainly don't want to be trying to draw that many in, right? And so, dealing with an infinite number of rectangles, well, we're going to be seeing some mathematical ways that we can find those. But before we deal with those, we have to get a new type of notation. This notation represents the area under our curve. And it's just a way of saying in notation the same thing that we've been talking about. The area under the curve of y equals x squared between 0 and 8. Yeah, it'd be good to write down this correlation between the words and that equation. One other little detail as you're writing it out, though. A reminder that when we say area under the curve, technically speaking, what we're really saying is the total area between the curve and the x-axis. All right, now that you've had a chance to write it down, let's take a look at exactly what's going on here as we write this out. This symbol here, this tells us area under the curve. That symbol must always be followed by that at the end. The d, typically it's dx because we're usually using x as our variable, but of course it could be other things. It could be dt, that'll come up a decent amount if our variable is t, but basically that's just showing that we're finding this area with respect to this variable. So that dx doesn't have any particular mathematical meaning outside of a notational meaning right now. All right, then as we write this, those numbers, the 0 and the 8. The 0 and the 8 represent our starting and ending values. The lower number is always the lower of the two numbers. So the 0 on the bottom must be smaller than the 8 on the top. And then whatever's in the middle, in this case the x squared, come on, the x squared there, that's always whatever f of x is. And so generically we'll call this f of x, but of course in this case it just happened to be x squared, or whatever our function is. We plug that in there. This formula, this notation, is called an integral. Integral is the formal name given to the area under the curve between the values a and b. All right, and now that you have this in your notes, basically we're going to be taking the rest of class, going through and seeing how this gets used, and seeing how this notation can be used to represent different situations. So to start with, this problem here, it hopefully seems familiar to you. We have this table of values, and of course our context up here, and you hopefully can scan through that and remember, because this was actually a problem off of your last assignment. And what it did is it had us find the rectangles. We drew in the rectangles and used those to estimate what would the total distance traveled be. Notice that by doing that, what you really did is this. By using that Riemann sum, and remember that's what we call it when we take those rectangles, find each individual area, and then add them all up together, those are Riemann sums. That what we're really doing is we're using that as a way to estimate the integral. And so I could have used this same notation that you see down here to represent that situation. The interesting thing, though, that came up on that and a couple other things that we've done recently is that very few people stop to question, why am I doing that with v and d? Well, we're going to take a deeper look at that. So here is a nice little piecewise function. I made it nice and simple, straightforward, I hope, so that we could find this area a little bit more easily. Because that's how we're going to do this, is if we're asked to find the total distance traveled and we are given velocity, we can actually do so with some areas. Let's see how and why. Let's start with this section of the graph down here. So you'll notice that what that is showing is that this person is, let's say they're driving, since this is 30 miles an hour, that would make sense. So this person is driving for 30 miles per hour for how long? Well, let's see here. 1 is here, so that means that this would be at a half then. So for half an hour, yes. Well, if you drive 30 miles an hour for half an hour, how far did you drive? 15 miles, right? Because we always multiply the 30 by the 1/2. That is miles per hour times hours. Notice that if we do that, you multiply 30 by 1/2, what you've really done is you have just found the area of this rectangle. You found the area under the curve in the velocity. And this actually works with all different types of velocity graphs, where if we know the velocity function, the area under the curve will tell you the total distance traveled, which means that I could also represent this situation using integral notation. And this is what we're really doing then, is if I want to find the distance traveled, I'm going to take my velocity function and I'm going to find the area under the curve between the 0 and 14 that we're working with here, because this person just drove from 0 to 14 hours. And that's how we can read this as well. It tells us between x equals 0 and x equals 14, find the area under the v graph, the velocity graph. And so that's what I'd like you to do here. Go ahead and find the area under the curve for this given velocity graph. And so I've written each of the widths up there on these rectangles to make sure that you're doing all right there. And so then to find that total, I then add each of those individual areas up together, and we should be getting an answer of 752.5. And we're actually talking about a real world type of situation here, so we do know the units. That'd be in miles. And so we are able to take the graph that we had, the information we had about velocity, and actually figure out what that total distance traveled is then by just finding the area under each one. Now this is the sort of thing you could do without knowing about integrals, but of course remember that we're going to be extending this into using integrals going forward as well, to where our graphs, well, they're going to have some weird shapes along the way, as we'd expect, especially with something like this. I made it a nice simple looking graph, but real cars don't jump from 65 miles an hour to 0 miles an hour in an instant. Unless something bad happened. So, yeah, even then we could get real technical. So, obviously, a real world graph is going to have a little bit more curve, a little bit more slant to it, some things like that. But this at least gets us into the area and actually understand kind of the basic idea behind it. Now, one thing to note, some detail-y stuff, is your graph could come out looking like this sort of a situation. Now, notice what this would mean. This would mean that we start with a velocity of 30 miles an hour for half an hour. So really what that means, remember, because velocity is a signed number, that basically means we are driving 30 miles an hour away from our starting point for half an hour. So then what this means down here, where we have the negative 30, is that we are driving for 30 miles an hour back toward our starting point. Well, think about it if you did that. If you drove 30 miles an hour for half an hour one way, turned around and drove straight back for at 30 miles an hour, you would end up back where you started from, right? That's what our integral here would tell us too. Is it would tell us that our total distance traveled is 0, because remember that distance traveled is not how far did I actually drive, but rather how far is it between my ending point and my starting point? And so we have to remember that idea when we talk about distance traveled. That's what it really means. We could take a very circuitous route to get there, but it's not going to reflect that. It's only going to reflect start to end. All right, now going back to the idea of a table. So this table gives the values of a function obtained from some experiment. We want to use them to estimate this integral using 3 equal subintervals with first right endpoints and then left endpoints. And I'd like you to go ahead and do this problem, practicing what we did in yesterday's work. As you take a look at this problem, sometimes people, when they're just looking at the original table, they get a little thrown off because there's 7 items up in the table. But we're supposed to be breaking it up into 3 pieces, and that can be a little bit of a brain bend. But remember, that just tells me which ends I'm going from, because notice I drew the number line down there to help visualize this. If I broke it up into 3 pieces, these are my pieces. And so you notice that in this particular example, at least, the odd numbers are the breaks between my rectangles. They're the breaks between my intervals. So the numbers I'm really going to be caring about then are these. And those are going to be the only ones that end up having any impact on the problem. I'm not even going to be using the 4, 6, and the 8, which already tells me I could probably get a better estimate if I did, but we aren't going into using all of those. We're only using 3 subintervals at the moment. All right, so to do part A, I need to use the right endpoints. Now, just so I can keep my own head wrapped around this properly, when I do my right endpoints, I'm actually going to start with the rightmost endpoint. The far right endpoint of this whole thing is the 9, 1.8. Now I want the height of the rectangle, that's the f of x, so I'm going to start with the 1.8. So I'm going to do 1.8 plus, and remember, I'm only needing the odds because of how this breaks up. So the next one's going to be at the 7, so that's going to be the 0.9. And then my next rectangle has a right endpoint here at negative 0.6. So then it's going to be, all right, plus a negative 0.6. But of course you could write minus 0.6 there. But if I just add them up together, that won't give me my actual area, right? I need to do one more thing to this, which is what? Yep, multiply it by the width of each rectangle. How wide is each of these rectangles? 2. Because you'll notice that basically we're going from 7 to 9. They're 2 apart. Or 5 to 7, 2 apart, and so on. And so then this is the actual calculation I'm going to end up doing to find my estimate for my integral. And so 1.8 plus 0.9 minus the 0.6 times 2 gives us 4.2 as the area under our curve. That is what we found by doing the integral. All right, and then we head on to part B, where we're going to be doing it with left-hand endpoints. For the left-hand endpoints, I'm going to start listing my numbers from the left side. So that means I'm going to start with my negative 3.4, plus, then I go to 5, so that's going to be the negative 0.6, negative 0.6, there we go, plus, and then we go to 7, so that's going to be the 0.9, and again, I'm going to have to multiply that by the width of each of those rectangles, so I'm going to multiply it by 2. And so we can now go ahead and do that addition and multiply by 2. That gives us a negative 6.2 as our integral value. Now remember that this is an approximation of our integral. So this is going from 3 to 9 of f of x of d of x. So this is what we're really finding here. But the big thing is that since we're using these Riemann sums, we're getting estimates for it. It's not the exact value of the integral, it's an estimate of the integral. Now in this particular case, Notice what we got is our two answers using our left hand and right hand sums. One answer was 4.2. The other answer was a negative 6.2. How confident are you in these estimates? Probably not a lot, right? And so with this problem, we're seeing some of the limitations of using those Riemann sums, and why, yeah, in our upcoming lessons, we're going to be having to figure out some ways to do it without having to draw lots of tiny little rectangles. Which, by that point, you'll probably be happy to no longer have to draw lots of tiny little rectangles.